I've called this video the use and misuse of statistics. And what we're going to be looking at here is examples where maybe looking at data in different ways might give seemingly contradictory summary statistics. And the choice of the summary statistic that you present to the world might influence how people think about the story behind that data. The stuff we are covering here is not particularly what we would call examinable stuff, if there was an exam. But exposure to these sort of stories will increase your data literacy skills, which means you can look at data analyses more critically. So the first thing we're going to look at is how maybe reporting numbers and reporting proportions might give two different stories to the data you're analysing. So consider the following example. Cardiff University has around 30,000 students each year. In 2018, 600 students dropped out. And then in 2019, 1,200 students dropped out. Two newspapers run the following headlines. So one runs, Cardiff University dropouts increase 100%. And the other runs, Cardiff University dropouts increase 2%. Which one's true? Well, in fact, you could consider both of these as true. 600 students dropped out in 2018. That doubled by 2019. And so there was an increase of 100%. What about this 2% one? Well, 600 students dropped out in 2018. That is 2% of the 30,000 students Cardiff University admits each year. It increased again by a further 600 students in 2019. So it increased by a further 2% of the student population. The two headlines here, one is reporting a multiplicative increase and one is reporting an additive increase. But just by looking at the proportions alone, we get two very ambiguous stories. The numbers themselves tell a better story here. Now we're going to look at some examples from those masters of deception, politicians, where they've done the opposite, where they have reported numbers rather than proportions in order to maybe deceive the public into what they've been doing. So both these examples come from this great article by Dr. Rid Lewis down below. So in 2019, Health Secretary Jeremy Hunt reported, compared to 7 years ago, we are treating 3,000 more people within the 4-hour standard. And this was for A&E, meeting A&E waiting list targets. And Jeremy Hunt reported this to show how well the government were doing. Look, we are treating more and more people within the 4-hour standard. But here he's only reporting numbers. He's not reporting proportions. Really, over the last 7 years, the numbers of people attending A&E had risen a lot. And so actually the proportion of people seen within the 4-hour target had dropped. Even though they were treating more people within 4 hours, the proportion of people they were treating within 4 hours had dropped. So in that view, they were actually doing worse than 7 years ago. Another example of this by Theresa May in 2017. She reported on spending. So she reported, the government is spending record amounts on education in England. So the government was spending more money than ever on education in England. But there she was talking about the number of money, the amount of money. Really, the real story was that much more pupils entered the education system. So even though they were spending more, there was more things to spend on. And so actually spending per pupil had decreased. So reporting proportions and reporting numbers here are telling us two different stories. Oftentimes we need to report both in order to give a more accurate account of what's going on. Here's a really neat story I like to tell, which really shows how useful or not useful summary statistics can be. In 1926, when aeroplanes were sort of first becoming popular, the US Air Force built a lot of airplanes and they had to design the cockpits for the pilots. And what they did was to ensure that they were all the same, but to ensure that most of the pilots were comfortable, they took the average measurements of all their crew, the average height, the average weight, the average width, the average reach to certain dials, the average amount they had to turn their head to see a certain screen and so on. And they built their cockpits so that everything corresponded to the average measurement. So the seats could take the average weight, they were the average width, so most people were comfortable. They were the average height, so most people were comfortable, and so on. Over the next 25 years, the US Air Force reported many accidents. And these accidents, when they talked to the pilots after, were put down to badly designed cockpits. And the US Air Force didn't understand what was going on. So they brought in an expert. They brought in 1950, Lieutenant Gilbert S. Daniels to investigate. Now, Lieutenant Daniels has a maybe unethical past, but it was useful in this situation. Lieutenant Daniels was an expert in something called typing, which at the time meant taking lots of measurements of lots of different people and being able to predict from those measurements how likely someone was to commit a crime. This is very unethical and is a pseudoscience, I need to say that. But he was an expert on measurements of people. His background specifically was in measuring hands, and he'd measured thousands upon thousands upon thousands of human hands from very diverse populations. And one of the things he did with these measurements was look at the averages, look at the average width of a hand, length of a hand, finger length, and so on. And one of the things he did with these averages was draw the average hand. He drew a hand which would have the average width, the average length, the average finger length for each finger, and so on. And when he looked at his drawing, he found that this hand didn't look like a hand. It was grotesque. It did not look like a hand. And what Lieutenant Daniels came up with was that there is no such thing as an average hand. Remember when we were looking at measures centrality, the average of a data set doesn't necessarily have to be in that data set. And when you have very skewed data, maybe that average really doesn't represent the centrality of that data set. And then Lieutenant Daniels looked at the measurements of the cockpits and concluded there is no average size of a US Air Force pilot. And so by building their cockpits to suit everyone, by building the most average seat, in fact, it suited nobody. Another thing I'd like to speak about, again with sort of what summary statistics are and the contrary views of them, is something called the inspection paradox, and there's lots and lots of examples of this. It crops up again and again. The picture I've used to describe the inspection paradox is this quite famous optical illusion where you can look at this one direction and what do you see? You might see a duck, and if you look at another direction, you might actually see a rabbit. And that's really exactly what the inspection paradox is doing. By looking at the data in one way, you might come up with a summary statistic, and by looking at the data another way, you might come up with another summary statistic, which seem really contradictory. They don't look like these statistics can actually make sense together, whereas actually that's what it's showing. And I can give you some examples of this. So imagine a university offers 7 classes, and there are 30 people in one class and 3 people in the other classes. The Chancellor of the university comes along and says, well, what is the average size of a class at my university? So he adds up 30 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3, divides by 7. And from the Chancellor's point of view, the mean class size is 6.86 per class. Okay, we've talked before about does that really represent the average class size? We've got skewed data here, but that is the average class size. Yeah? When the students saw this in a prospectus advertising the average class size, they thought, well, this doesn't represent what I'm seeing in campus. So what they investigated, and they investigate by going around every person in the university and asking them, what's the size of your class? And they recorded all these. But when they are doing this, the students themselves don't see the image you've got here. What the students see is 30 people with a class size of 30 and 18 people with a class size of 3. So now when they add up all these class sizes and divide by how many are there, from the student's point of view, the mean class size is 19.88. It's very, very different to the Chancellor's point of view. So again, by looking at exactly the same data in two different ways, we get two contradictory summary statistics. Why? Well, one of the reasons here is that very thing that you are measuring, class sizes, affects how many observations you've got. So a class size is a group of observations. The bigger the class size, the more observations you got. So that very thing you're measuring affects how many observations you got. Why does it always feel like buses are late? This is because of the inspection paradox. So I've drawn a timeline here, and I've drawn a timeline going from left to right, and I've said, when do the people arrive? So the people represent on the timeline when they arrive to wait for a bus, and it's sort of evenly spread throughout the timeline. And I've got when do the buses arrive, and they are at exact intervals on this timeline. If we ask, what's the probability of waiting longer than average on a bus? So I've coloured in red the people waiting longer than average, and I've coloured in green the people waiting shorter than average for a bus. In this case, we get 23 people waiting longer than average out of the 46 people. That's 50% of the people are waiting longer than average for a bus, which is exactly what you'd expect. What happens when a bus is late? When buses start becoming late, well, actually now, the mean waiting time for the bus hasn't changed. There's still 5 buses arrived in that same period of time. The average waiting time for the bus has not changed. But now, more people are waiting longer for the bus. Why is that? Well, again, the thing you are measuring, like how long you wait for a bus, is also how many people are going to fall into that long gap waiting for a bus. The longer the gap, the more people there are to fit in that gap to wait for a bus. And there's a longer time window for them to arrive in to wait a long time for the bus. So even though the average waiting time for the bus hasn't changed, more people are waiting longer. And that is, again, because of the inspection paradox. These two summary statistics, the average waiting time and number of people waiting longer than average, seem to contradict each other. A very famous example of the inspection paradox is called itself the friendship paradox. And the friendship paradox is when you have a network of friends, and this little diagram here of a network represents a particular network of friends. Circles represent people, and links between them if they are friends. And what the friendship paradox says is that on average, your friends have more friends than you. How is that possible? Well, if we think about this setup, how many friends does everyone have? So I can label every person, how many friends they have. So for example, this person here has 5 friends, 1, 2, 3, 4, 5. This person here only has 3 friends. This person here only has 1 friend, and so on. Now we can ask, well, think about this person with 5 friends. On average, how many friends does his friends have? So this person has 3 friends and 2 friends and 3 friends and 1 friend and 1 friend. Add all them up and divide it by the 5 friends that he's got. So that's 10 divided by 5. So on average, his friends have 2 friends. And he himself has 5 friends. So for this particular person, on average, his friends have less friends than him. But if we do this to everyone, what we find actually is that 75% of the people here, their friends have more friends than them on average. And this seems really unintuitive. Like, how come so many people have friends who've got more friends than them? Surely the numbers don't add up there. Lots of people whose friends have lots of friends would mean there's lots of people with lots of friends. But no, actually, because again, the inspection paradox comes in here. What we are measuring, the number of friends, affects how many people you are looking at. So this person with 5 friends, yes, he has 5 friends, but there's also 5 people all looking at him. And so 5 people are all looking at that same data point. So as soon as you get one person with a lot of friends, there's a lot of people looking at someone with a lot of friends. And that's where this paradox comes in. Why might this be important? There's no sort of calculations or adjustments we can do about this, but it's important because when we start reading statistics, we need to consider, is there an inspection paradox going on here? So for example, a recent census shows that 50% of households in Manhattan consist of just one person. So that might be really tempting to go, well, actually, that means 50% of Manhattan residents live alone. But that's not true. 50% of the households containing just one person means that the other 50% of households contain at least 2 people. So at the worst, only a third of Manhattan residents live alone. So we've got 2 statistics here, the percentage of households containing just one person and the percentage of residents who live alone. And it's really tempting to say they are the same thing, but they are not. They are looking at the data in different ways, and so they're going to be different things.